Hi everyone. So I just wanted to quickly wrap up the presentation where we left off. So we were talking about collisions, or we were going to talk about collisions. We just finished the explosion example of the kickback of the rifle, right? So when it comes to collisions, we're actually going to have two main categories of collisions. The first of which is called elastic collisions, and the second of which is inelastic collisions. So what an elastic collision is, so sorry I'm kind of emphasizing it, it's kind of tough to say elastic because it sounds a lot like inelastic. So in elastic collisions, that is a collision in which momentum and energy are conserved. On the flip side, we've got inelastic collisions, and that's where momentum is conserved but energy is not conserved. Okay. So a helpful hint to remember which type of collision energy is conserved, I like to think of that dealing with elastic starts with an E, energy starts with an E, so in elastic collisions, energy is conserved, right? And then in is the Latin prefix that means not, so inelastic means not energy conserved in my brain. Maybe that helps you, maybe it doesn't. So delving more deeply into inelastic collisions, the reason why energy is not conserved is that during the collision, so when these objects collide or interact, this kinetic energy is converted into some other form of energy. A lot of times when these objects collide, they're going to change shape, even if only slightly. And this change in shape, you're dealing with stretching and compressing bonds between atoms, and that uses energy. So the system is going to lose energy doing this. Just on a side note, in the real world and everyday world we're dealing with, almost all collisions are inelastic. The most elastic we're going to be dealing with in the real world is actually when we're dealing with an ideal gas, even though ideal gases are not really a thing either. But we're not going to worry about that in this class. But energy is lost in these types of collisions. So here's the little diagram of what's kind of going on. So here we have two objects colliding. So before the collision, they're moving towards each other. After, here in this situation, these objects are moving away from each other. But we have some energy lost here due to sound or heat. Right? I don't know why they use the word X and J during that explosion. I have no idea. But some typical situations for inelastic collisions. So the first of which is when two objects collide and they stick to each other. Okay? This situation is always going to be inelastic. It's actually called a perfectly inelastic collision. So when you have two objects coming together and they combine and stick together, this is called perfectly inelastic. The reason why it's called perfectly inelastic is because it has the maximum energy loss. Another type of inelastic collision is going to be an explosion. I mean, it's not really a collision, right? It's an anti-collision. It's the object coming apart. But the reason why I included it on the slide is because energy is not conserved when an object explodes. And then finally, another type of situation that could be inelastic, not necessarily inelastic, right? If we have objects coming, they interact, so objects come together and they bounce off each other, right? So this type of interaction could be elastic or elastic or inelastic, but if energy is lost during this situation, this is an inelastic situation. Right? So elastic situations are always going to be objects bouncing off each other, but it's a situation where energy is conserved. So in order to tell the difference between this situation and the inelastic on the previous slide, you actually have to do the calculation to see if energy is conserved. The AP exam loves doing this type of problem. I believe, and I don't remember if it's the most recent exam or an exam a couple years ago, but they did have free response question which asked exactly this, right? They asked whether, and we had some sort of collision here, and they asked whether energy is conserved or not. Okay. We already did this example in class. So here is a ballistic problem. I'm not doing this example in this PowerPoint here. or in this recording here, I do have a separate video which I've also uploaded with this solution. But actually talking about this problem, this type of problem is very popular in the fact that you have to use both energy conservation and momentum conservation to solve it. AP exam loves that stuff. And then finally is dealing with momentum in two-dimensional collisions. So when we have a two-dimensional situation, momentum is still going to be conserved. Right? So in these collisions, the individual momentum of each object can change, but the total momentum does not change. Right? So we can break up the problem into the conservation of momentum in an x direction and conservation of momentum in an AY direction. Right? And that total momentum will be conserved. And this is a very helpful tool in solving these more in-depth, more complex problems. So here is an example. I also show solution work through an example, this example here for you guys. If you go, I also have uploaded, this is actually a two-part video, and even in those two parts, I did not solve this final question of how the final kinetic energy compares to the initial kinetic energy. I trust that you guys are smart enough and can figure that out with what we learned with energy and how to solve for energy and doing energy calculations. All right, thank you.